Welcome everyone to this fourth video in set of videos here on chapter 14, Chemical Kinetics. In this video we're going to talk about reaction mechanisms. Okay. So what is a reaction mechanism? A reaction mechanism is a step-by-step description of how your reaction's actually taking place. Okay. When we write up chemical reactions here in chemistry, okay, we talk about what is the reactants and what are the products. Okay. Well, it's not always the case that those reactants collide together and form the products in one simple step. Okay. Often, in most chemical reactions, there are multiple steps that lead us from the reactant to the product. Okay. And those different steps we call elementary steps. Okay. They are single steps in what's called a reaction mechanism. Reaction mechanism, again, describes how we get from the reactants to products in a set of elementary steps. Okay. Often in these elementary steps, we will form intermediates, which are compounds that are formed during the reaction mechanism, right, while the reaction is taking place, but then consumed in order to eventually produce the products. Okay. So intermediates, they're called intermediates because they only live for an intermediate amount of time, because they're formed during the chemical reaction and then consumed during the chemical reaction and don't exist before or after the chemical reaction takes place. Okay. Like the reactants and products do. Okay. And so all that we've been talking about so far in terms of these kinetics and these rate laws and integrated rate laws, right? These are all related with the study of reaction mechanisms, okay, and the study of how chemical reactions are actually taking place, how things are reacting, okay? Because if we can understand what is the reaction mechanism for some chemical reaction, we can try to optimize that reaction, or we can try to stop that reaction from happening using the information based off the chemical reaction mechanism, right? This is done all the time in biochemistry, right? In pharmaceuticals, right? Pharmaceutical drugs, right, are designed typically to enable or inhibit certain chemical reactions, and the way they are able to determine, right, how to do that is by understanding the reaction mechanisms that they're trying to stop or increase. Okay. So for example, right, I could write this chemical reaction NO2 plus CO going to NO plus CO2. Okay. But this reaction doesn't actually take place by having NO2 and CO collide and transferring an oxygen to form NO and CO2. Right. The actual reaction that takes place, okay, is through this proposed mechanism here, where I have NO2 colliding with another NO2 to form NO3 and NO. Okay, so these two NO2s collide in space. They transfer an oxygen to form NO3 and NO. NO3 here then collides with a CO to form NO2 and CO2. Okay. Now NO3 is what will be called an intermediate, right? Because NO3 is produced in my reaction mechanism and consumed later on. If you add these two reactions together, you will get the total chemical reaction up here. Okay. If I add these two things together, I will get that total reaction up above once you simplify. Okay. And that has to be the case, right? Your reaction mechanism, the elementary steps that make up your reaction mechanism better add up to give the overall chemical reaction. Otherwise, it is not a valid reaction mechanism. Okay. And the rate of this reaction is given by KNO, or the rate law, sorry, is given by KNO2 squared. Okay. And we'll talk in just a minute in this video about how we determine the rate laws of from reaction mechanisms. Okay. Right. In these mechanisms, in these elementary steps, we can describe an elementary step by its molecularity. Okay. A molecularity is just how many molecules collide for that elementary step. Okay. So unimolecular reaction is when there's just one molecule. Okay. This is often the case in like nuclear decay, right? But can also involve a molecule colliding with a wall or something like that, right? In order to initiate some sort of chemical reaction. Okay. Bimolecular reactions, right? Two things have to collide. And termolecular reactions, right? Elementary steps require three things to collide, right? And this is very rare just because of the fact, right, that for three things to collide in space at the same time is very unlikely to happen, okay? Right, if I have three different molecules bouncing around in space, right, these things all have to reach the same point at the same time for this reaction to take place, and that just is very infrequent. Okay. So the rate law from a elementary step is directly written from its molecularity. Okay, so what does that mean, right? So here I have an elementary step, right? This is an elementary step, right? The rate law of this elementary step is just equal. It's just the rate equal to the rate constant times the concentration of your reactants together. Okay, right? So concentration of NO2 times concentration of NO2. If I had more reactants, I'd keep on plugging them in, right? And this simplified, right, is just rate equals K times NO2 squared. Okay? And so this is the rate law for this elementary step. Okay? And we can write the rate laws from elementary steps based off their molecularity because, again, an elementary step is telling you how things are actually colliding. I know for this reaction to occur, an NO2 has to hit another NO2. So it's going to depend on the concentration of NO2 and the concentration of NO2, right? Which gives us this concentration of NO2 squared. Okay. Right, and so again, these reaction mechanisms, right, are these series of elementary steps that sum together to give the overall reaction, okay? And this mechanism, the rate law from your mechanism has to agree with the experimental rate law, okay? Otherwise, that mechanism is not true, okay? And this is what's done in the lab all the time. People propose mechanisms for a chemical reaction. They then use experiments to determine what the overall rate law is for that chemical reaction and try to see if the rate law from their mechanism agrees with the experimentally determined rate law. Okay. So in this class, to help figure out what the rate law is from our reaction mechanism, we'll often use what is called the rate determining step kind of approximation. Okay, the rate determining step, right? What this is referring to is often in some chemical reaction, there's some slowest step, okay? In some mechanism, right, I have multiple steps, right? One of those steps is going to be much slower than the rest, okay? That slow step is the rate determining step, okay? And that slow step will, as this is saying, right, determine what the rate is for your overall chemical reaction, okay? So again, right, think of evacuating a building, right? Everyone can clamor to the door in order to evacuate the building, but then only so many people can fit through the door. So fitting through that door is the rate determining step, and the speed at which people can leave the building depends on how fast people can go through that door. Okay, right, and so the same thing for a chemical reaction. I have multiple elementary steps. The slowest of those elementary steps will determine the overall rate of my chemical reaction, right? So the rate law of that slow step is equal to the rate law of my overall chemical reaction. Okay. So, for example, right, going back to this original example of NO2 plus CO going to NO plus CO2, right? Experimentally, I know the rate law is the rate equals K times NO2 squared, right? And if I have this proposed mechanism here, okay, where I know the first reaction is the slow one, okay? So this is my rate determining step, okay? This first reaction, right? Well, the rate from this first reaction is just rate equals K times concentration of our reactants, right? NO2 times concentration of NO2, right? Which simplified is just K times NO2 squared, right? Which disagrees with the experimental determined rate law. So this reaction mechanism seems like a valid reaction mechanism for this chemical reaction, okay? Because the elementary steps add up to give the overall chemical reaction, and the mechanism, the rate law from that mechanism, agrees with the experimentally determined rate law, okay? So, right, just note that intermediates do not appear in the rate law, okay? Intermediates should never appear in the rate law, okay? And we only want reactants or products in our rate laws, right? And again, intermediates don't appear because, right, they're formed and consumed during the overall chemical reaction. So they only exist temporarily. So our rate law should never depend on the concentration of NO3, which is an intermediate. Okay, right. Now, I talked about, right, that once you determine the rate law of the chemical reaction, and the rate law of your mechanism, right, that kind of validates that mechanism, right, but we can never prove exactly that that is the actual reaction mechanism, right? We don't have a way to zoom in and view and visually inspect and determine what is reacting with what and how they're reacting, what atom is moving where, when, in a given chemical reaction, right, to verify, to prove the actual mechanism, okay? Right? I can easily disprove a mechanism, right? If the rate laws don't agree with the experiment, then I can disprove my mechanism, right? But there could potentially be multiple mechanisms that have the same rate law that agree with the experiment, right? And then it can be difficult to determine which is the actual mechanism, and one might need to do further studies to try to determine it, and you might never be able to figure it out, okay? Right? But so you can never prove for sure this is 100% what the mechanism is for a chemical reaction, but we can get to a fairly good certainty, right, at some point. And that's it for reaction mechanisms and this video.